All right, welcome back. One more to go. We're going to talk about here rate laws. So a rate law is an equation that summarizes the effect of concentrations. And so for a generic reaction, AA plus BB going to CC plus DD, it looks like this. So the rate of the reaction is equal to this K, A to the X power, the concentration of A to the X power, and the concentration of B to the Y power. So what are all these things? K is called, imaginatively enough, a rate constant, and it is different for each reaction and actually each temperature. X and Y are exponents that bear no relation to the coefficients for that species in the reaction. And they are not even necessarily whole numbers, although they usually are, somewhere between 1 and 3. Now, the rate constant and those coefficients are determined experimentally. And the result is that if you plug in the concentration, any particular set of concentrations, and work everything else out, you will get an answer that tells you what that reaction rate is going to be at that instant with those particular concentrations. So what we're going to do now is talk about basically how we determine that. And it's something called an isolation method. And what we do, and so this reaction here is 2 nitric oxides reacting with 2 hydrogens to form an N2, a nitrogen molecule, and water. Now the rate is going to have the form, the rate constant times the concentration of NO to some power times the concentration of H2 to some power. So only reactant concentrations go into experimental rate laws, not products. And we determine the rate constant and coefficients with things like this. This is a set of 3 experiments where I have changed the initial concentration of nitric oxide and of hydrogen, this is all moles per liter, and measured the initial rate, the rate at the very, very beginning of the reaction. And again, so this has units of molarity per second, so change in concentration, change in time. And so how do we use this to figure it out? Well, the idea is we want to look at a set of experiments where only one concentration is changing, the concentration of one component is changing, and the other one is remaining constant. And we see what effect that concentration has on the reaction rate, and that tells us what the exponents are. So how do you do that? Well, let's give it a shot. So think about, a set of reactions. So let me ask you, what set of reactions are going to tell us what the H2 exponent is? So hopefully you came up with 2 and 3, and that is simply because that the concentration of NO is constant. So this guarantees that any change in the reaction rate is due only to the change in the concentration of H2, because that's the only one that changed. And how do you do this? It's pretty straightforward. The concentration of H2 is obviously doubled in those 2 experiments. And the experimental rate is often shown to double. So the way that you do this is you just take the factor by which the concentration change and the factor by which the rate change, and then ask yourself what value or what exponent will make that true. And the answer is 1, so 2 to the first power is 2. And that tells us that, all right, so in case the audio cut out in this slide transition, In the last slide, we did figure out that the exponent for the H2 was in fact 1 because 2 to the first power is in fact 2. So now we need to figure out what the NO exponent is. And what we need to do is find a set of experiments where NO is changing, but H2 is not, their initial concentrations. And that is in fact experiments 1 and 2. So in that experiment, the concentration of H2 is held constant and the concentration of NO is doubled. So let's look at that now. So what is that exponent? So the setup is, and the rate you can see here actually quadruples. So the rate goes from 1.25 times 10 to the negative 5 to 5 times 10 to the negative 5. So that is, so again, if you wanted to find that, if you divided this one by that one, you would get 4. So that's how you know it quadruples. So the setup here is that so again, the concentration change is a factor of 2, and the reaction change is a factor of 4. So 2 to what power is 4? And that hopefully is, is 2. So 2 times 2, or 2 squared, is 4. And that tells us that the rate is going to be equal to some constant times the concentration of NO squared and the concentration of H2 to the first power. So the one thing we need to know, the one last thing we need to know is what is the value of that rate constant K. So how do we figure that out? Well, now that you know what the exponents are, before I do that, in this class we don't care about this too much, but this slide actually tells you exactly what the proper mathematical setup for determining the coefficients are. But I will give you the examples that you'll see in this class are usually it's either first power, second power, it's squares, or third power, it's cubed. But take a look at this if you are so inclined. If you are not, now back to figuring out K. It's pretty simple. Once you've determined the exponents, pick any experiment. I usually pick the one in the middle. And simply solve for it. So this is just rearranging this equation right here to a form that says K equals, and it's going to be the rate divided by the NO squared and the H2 to the first power. And you know all of those things, just read them up from here. So we've got 5 times 10 to the negative 5th meters per second divided by 0.01 molar squared and 0.002 molar. Don't forget to square it. That's one of the most common mistakes. And if you do that, you get a rate constant of 250 inverse molar squared inverse seconds. That could also be written as 250 molarity to the negative 2 seconds to the negative 1. So mental note, rates always have the same units, which are molarity per second or molarity per second. The units of the rate constant will vary depending on these exponents because you're going to have a different number of molarity terms. Fun fact. A couple other things. We often talk about reaction order once we have this reaction. And that often just gives you the numerical value of the exponents. So this particular rate law is first order with respect to H2. It's second order because that exponent is 2 with respect to NO. And there's also another one called an overall, which is just the sum of those two. So this is the third order overall. All right. And that's how you determine this. That's how you determine a rate law. Now what I'm going to do is this slide here is a workup of another example. Now you'll have a a quiz slash assignment question about this. And this is, you will not see one harder than this on an exam. So if you can work your way through this one, you should be fine. And I hope to see you next time in Zoom class. Take it easy.